The world we live in is one of constant innovation, progression of technology, and blurring the lines between the real and digital world. For decades, humans have advanced the interfaces with which we interact and observe. Keyboards, mice, touchscreen, incandescent, CRT, LED VR. But our abilities are limited by the methods we use, our hands and muscle movements for inputs, and our eyes, ears, and other senses for observation. In this age, that is the point of stagnation. There's only one next step that will propel humanity into the future, and that is a direct interface with the brain. Some of the first attempts at this were simple and non-invasive electrodes to sense and record brain signals through the skull and skin, called an electroencephalogram, or EEG for short. Although, as you may guess, this method is generally inaccurate and not particularly useful for the applications we are interested in. Although, if you are interested in experimenting with your own brain-computer interface, it is still the easiest method. EEG devices are non-invasive. This means that they passively use electrodes which sense brain activity from outside of the skull. It is clear this is not good enough. Invasive methods have already long been researched and tested within animals and now even humans. The method we will be talking about today is the microelectrode array. Composed of a grid of electrodes, it is surgically implanted in the brain, with some of the better systems such as Neuralink connecting each electrode to specific neuron groups, though this is not particularly necessary. This essentially allows for real-time sensing of many extremely specific areas of the brain, making it far easier to control things digitally. This method also opens up a new ability, that is, the possibility of not just sensing, but also creating electrical signals with which we can input data directly into the brain. Not only could this be used for general information, it could also re-enable or add new senses, such as vision or sense of touch with prosthetics. Past systems have been large and conspicuous. It has also largely been an issue deciding how the computation should be allocated. In years when data processing was difficult, even by a large computer, massive cables were utilized so that every connection could connect to the computer in parallel. Systems like Neuralink have advanced to the point where much of the data processing occurs inside the device itself. This is by far the most expensive option though, as they utilize completely custom silicon chips with advanced machine learning algorithms. Today I will not be creating my own silicon, unfortunately. Maybe in the next video, but in this one we will be creating custom PCBs, firmware, and allow for the creation of an entire technological ecosystem, infinitely expandable by the open source community. Starting off, let's identify some dimensional constraints. As stated before, it needs to be quite small. The back of the skull, near where the spine connects, is the thickest part on average, so ideally that is where it should be implanted. This would allow for the device to have as much hardware as possible, while still remaining in the same general size footprint your head already does. I believe it is also quite important to be able to fully remove the device without any form of surgery, just a simple screwdriver, to allow for extremely simple maintenance and installing custom expansions. So I decided I would make it a circular shape, about 20mm in diameter. Now it would be essentially impossible to do anything with that scale, so it is actually a stacked design, making use of that depth of the skull. Each layer can be connected by spring pins to allow for electrical contacts and data transfer between layers. Another important constraint is that I want any connector to the device to be easy to connect without looking, durable, waterproof, and compatible with a current standard. While it does have its own shortcomings, I've always admired the 3.5mm audio connector. It allows one to easily plug a cable in at any orientation and can rotate freely. It also has a number of siblings of different sizes and standards, but it is usually used for analog signals. It was originally invented for phone switchboards in the late 19th century, but is now most commonly used for headphones and audio equipment. It would not be applicable to use for a brain-computer interface application though, for a number of reasons. The first is that it is too long, even with the shortest being about 1 centimeter in length. We are putting the device on the back of the head, so we do have roughly this depth to work with, but we have other issues as well. If the connector itself fails by breaking, it does so not safely. Those of you who have had a headphone connector break off inside a device would know, it is difficult to remove or replace. So instead of making our connector have pads around a cylinder, we can flatten them, creating a circular connector. This way, all of the connections happen at the surface, and the connector can freely rotate. The cable side will just be a flat PCB for simplicity, and the device itself will have a spring connector connecting to each of the pads, with a single pogo pin for power in the center. I decided to make this compatible with USB, so it contains 4 total connections, for ground, power, data plus, and data minus. This will make connecting to computers and accessories easy. Yes, but it will also allow adding expansions by treating them as USB devices. Working backwards from the cable, it will connect to the device's PCB stack through a placeholder riser. This is a layer that just increases the height of the stack, so that in the future you can swap in an expansion device. After that, it connects to the main board of the device. The purpose of this board is to handle all inputs, accessories, USB devices, and read the BCI data. I use an Atmega32U2 microcontroller for this purpose because of its built-in USB support, but ideally this role should be delegated to a more powerful processor in the future. The 32U2 is a smaller and slightly less capable little sibling to the Atmega32U4, which is used for things such as the Arduino Pro Micro. It is also important to note that this is the last layer to use USB. This is because the next parts not only require more data pins, and it would be a waste of time and space to add another USB chip, but it also is quite an essential component, so really should not require separation beyond this point unless damaged or an upgrade is needed. This may change in the future as well, just to allow more modularity anyway, but currently these connections I've decided to be completely hand soldered. This video is made possible by JLCPCB. They provide easy, affordable, and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. JLCPCB features a number of services from PCB manufacturing to plastic and metal 3D printing and CNC machining. I've used them for a number of years and have always been impressed by both the quality and accuracy in the parts I receive, all for low cost. Simply upload your files, get an instant quote, and receive your parts a week later, and get $30 off with a coupon and enjoy top quality 6-layer PCBs. Try JLCPCB today and get 1 through 8 layered PCBs made for just $2 with turnaround in just 24 hours. Click the link in the description below. The main board, and all of the other boards for that matter, only use surface-mounted components. This is without question for an application of this scale, but some of the parts or their connections are so small they are difficult to see with the naked eye. As such, it took a number of attempts and resoldering after using the solder mask to get each part to a working state. That is also the reason much of this footage is actually filmed through a digital microscope from my university, which was invaluable. This project is reaching a scale where it is likely more economical and time effective to have all or most components soldered by a pick-and-place machine, where the PCBs are fabricated, at JLCPCB. At this point, we want to program the microcontroller. I left pads on the back of the PCB for programming with ICSP. It is possible to just press the pins of the programmer against these pads, but it is easier and probably safer for the microcontroller to just solder a temporary header. I used a programmer called USB ASP, which made the process of uploading quite easy using AVRDude. I utilized a library called Lufa to communicate over USB, and edited the example serial demo written in C to send data. I also need to change values in the make file, specifying that I am using a 16 MHz external clock, and that I'm using the Atmega32U2. I used this command to upload, and it should now be working. Before I can test if everything is functional, I need to make the cable. I used a sacrificial USB-A cable, spliced the end, and passed it through a 3D printed connector end I designed. Then I soldered it to the circular male PCB and tightened the screws to hold it in place. But after connecting everything, all I got was an error in Windows about the USB device malfunctioning. I spent many hours looking at the PCB under the microscope, trying to find bad solder joints, resoldering components, checking values, and even completely replacing the microcontroller. Despite any soldering issues, the main problem I encountered was staring me in the face the whole time. I'd somehow accidentally mixed up my data plus and data minus pins on the motherboard, so USB was obviously not working. Luckily though, this did not require reordering the PCBs, as I could just swap around the connections on the custom USB cable I made. Part 2. Data. Data powers the modern world. Data transfer. Messenger, horse, car, train, telegraph, phone, internet, fiber optic. USB is a serial communication protocol which succeeded its predecessors of yesteryear, the serial and parallel ports. It utilizes 4 wires: ground, power, data plus, and data minus. The data cables allow back and forth communication from one device to another. A mind link becomes a peripheral to a computer, your computer a coprocessor to your brain. Yes, this method is simple for data transfer and expansions, but it has downsides. Waterproofing would be nearly impossible. It also leaves much to be desired in terms of security, since the main controller to the device in your brain is directly exposed and could be damaged or reprogrammed too easily. So there's another type of connector to be used. This one is also not standardized, but my own design. It utilizes magnets on the connector end, which is connected to ground, with a center spring pin either for 5 volts, data plus, or data minus. Yes, this cable is also somewhat compatible with USB, but with 3 identical connectors, each for a different purpose, just wiring it directly to a computer would result in a short circuit or other unexpected behavior 5 out of 6 times. So the way it functions is actually by making each connection not have a defined purpose until all wires are connected, after which the MindLink will negotiate what wires are connected to which connector and switch accordingly. And because these connectors utilize magnets, it is easy to connect and disconnect as needed. They are also naturally waterproof because the entire connector is exposed at the surface and it waits for a signal from the computer before sending any amount of voltage through the connections. At this point, I have yet to mention how the MindLink interfaces with the brain. While it is as yet impossible to surgically implant custom brain hardware while in my garage, we can assume everything on the neural interface is ideal. For this version, I set the neural matrix size to have 32 electrodes. This number was relatively arbitrary and could be anything. We assume everything on the brain side is taken care of already, and all of the electrodes are connected to a base plate PCB. Now on the MindLink side, we have a new layer. This will have spring pogo pins to match the pads on the brain baseplate. Of course, at this point, it is probably clear that the Amiga32 microcontroller would not have enough pins to properly accept all 32 of these inputs. To do this, 4 multiplexers will be placed on the other side of the same PCB, each selecting between 8 of the neuron matrix's pins. There's now not much space remaining on this layer, so to continue we should add another and expose the required pins. Another multiplexer will be used to select between the outputs of the first 4 multiplexers. At this point it would require 7 pins to address the individual pins in the matrix, and 1 pin for the output. Even this is too much for the microcontroller, although there does exist an easier method. Instead of addressing from the microcontroller, we will offload that duty to a counter IC. Each time we wish to see the output of a neural electrode, we send a pulse to increment the counter by 1, selecting the next pin with the multiplexers. It is now impossible to know which exact pin is selected, so another connection can be used to send a reset pulse to sync. Now there are a total of 3 connections to the microcontroller: the analog input, the counter incrementer, and the counter reset. It is also important to mention that on the second board, there is an op-amp to amplify the voltage to 5 volts from the incoming neuron, since they typically send pulses of only about 0.15 volts. Now each electrode can have its value read by the microcontroller and sent to any device. I use processing to create this visualizer. In a full application, this data would also be processed with the machine learning model, so the activity could be understood and actually used. I then 3D printed this proof of concept cover and mounted the MindLink. As you can see, it conforms to the shape of the skull, and has many screw holes for mounting and holding peripherals. The MindLink is also completely flush with the surface, so there are no protruding pieces. And now, taking a look at the entire thing, it is constructed primarily out of plastic. This is wrong.
Part 3.
A tooth is pulled. A steel replacement is installed. The material begins to leach into the surrounding flesh and bone. The immune system responds to the medical implant by attacking it. Inflammation, irritation, eventual removal. Most materials humans know of are not biocompatible, though there are a few, such as titanium or zirconium oxide ceramic, which are almost completely inert in the human body, having no reactions with tissue and not being attacked by the immune system. Most likely titanium would be the best option for the MindLink. Not only is it easier to manufacture, I can even have it 3D printed for only a few dollars, but it is also more ductile and less likely to shatter in the case of a large impact. Although I'm not trained medically, so it may be the case that I am wrong on each of those points. Otherwise, a ceramic would be much better because it would not block Bluetooth or Wi-Fi signals like titanium, and also be non-conductive, so extra shielding would not be necessary. Once the MindLink is implanted, it makes sense to just leave the entire thing exposed. This would allow for very easy access for maintenance or upgrades. But because it is a design that doesn't take up more space than the original skull did, it would technically be possible to have skin still over it, though you would still be limited to what haircut you have unless you choose to not plug it in often. So in the future, it would likely be more popular to have removable silicone or plastic covers. The MindLink as it stands is no more than a proof of concept. There is a long road ahead to take it from a stack of PCBs and 3D printed parts to a fully realized and truly seamless brain-computer interface. But I believe that we should go there together, that the future brain-computer interfaces should be accessible to everyone through open source and as customizable as possible. Even if what is eventually adopted is completely different from this, I hope it stands as a basis for future work. Thank you for watching.